All right, let's get started. So we have been talking about section 8.6. I don't know if there's actually any videos specifically over 8.6. I don't think so. And the reason for that is really there's not a lot of new stuff in 8.6. 8.6 is just a chance for you to practice, in some sense, what you'll have to do on the exam. And that is diagnose the problem and then integrate, where up till now it's kind of like, hey, in the partial fraction section, guess what? You need to use partial fractions. So it's not a big surprise. In this section, the challenging part is what do you use, right? And so I think that maybe a good way to spend our time today is we could look at some problems and I could help you think through, well, what technique might you try? And maybe we'll work some, but I think that it might be more helpful to you in some ways if I just help you to see, okay, what's even the first step of this problem? And so let's get started. Did you have one?
No, I had a question.
Sure.
Because tonight 8.9 is due, or?
No, I changed things around a little bit, and I'm sorry that I didn't get it done Friday night, but I had announced that I was going to make 8.6 due tonight, and I changed that today. So 8.6 is due tonight. Then we skip over for sure 8.7 and 8.8. And then we go into 8.9 on improper integrals, and there are two different assignments on improper integrals. The first one will be due Wednesday. The second one will be due Friday. And then next week will be our second exam over chapter 8. So tonight, all that's due is this section 8.6. And if you're really ahead and you already turned in 8.6, I guess, well done. Yes.
Would the exam be next Monday or next Friday or next Wednesday?
Right now I'm thinking that the exam will be on Wednesday.
Okay.
So we'll do kind of a review day on Monday and talk about the exam, what to expect. And then Wednesday will be the exam. Yeah. Yeah.
Number 7?
Sure. Number 7.
Just on how to, how to people.
Yes. Okay, yeah. So number 7. We have the integral from 0 to pi over 2 of sine theta divided by 1 plus cosine theta d theta. And one of the things that definitely makes any of these problems hard is now we have a lot of things we could do. And so deciding which one to do is sort of difficult. Oh, square. That was a square, right? Yeah. So what do you do? Well, one thing that I see right off the bat that is at least interesting to me is that the derivative of cosine has something to do with sine. So I think, well, what if I just substituted it out then? So let's let u be cosine of theta. So du is negative sine theta d theta. And so let's just see what happens if we make this substitution. I need a negative. So that means I'll add a negative on the outside as well. And now I can rewrite this as negative integral of, on top I just have du. So if you like, I'll just put 1 du. And on bottom, I have 1 plus u squared. And now I can change my limits of integration. Let's see, if theta is 0, cosine of 0 is...
Can I ask a question?
Yes.
So I guess I was under the impression that in order to do that, I would have to use 1 over cosine of 2. Do I not have to do that? Because the cosine is at the bottom.
Yeah, it's okay.
Okay.
It's okay to use something on the bottom as u. It's not okay to have something on the bottom be du.
Okay.
Okay, so it's okay if I use something like cosine to be my u. Yeah, that's okay. Yeah, and so at this point, well, I could rewrite this. This is 1, correct? And then if I plugged in pi over 2, I get 0 here. But now, what is that antiderivative? Can anybody tell me? Yeah, tan inverse of u, right? And so this, at that point, isn't that bad. So this is just minus tan inverse of u evaluated from 1 to 0. And you can go from there. Yes, sir. Oh, maybe you weren't raising your hand. Never mind. Yeah.
This is just a side note. Are those like integrals, like the tangent inverse, is that derived from a trig stuff? Like into the interval?
So how do you get that the antiderivative of 1 over 1 plus u squared is tan inverse of u? Yeah, it's a good question. So where it comes from is, do you remember in calculus 1, you do implicit differentiation? Do you remember implicit? Okay, so if you have like tangent of x is equal to, tan inverse of x is equal to y, let's say, and I want to know what's the derivative of y. In other words, what's the derivative of tan inverse of x, right? Well, I can say, okay, I don't know the derivative of tan inverse of x, but I could say that x is equal to tangent of y, correct? And now I could use implicit differentiation to take the derivative of both sides. If I do over here, the derivative of x is just 1, and the derivative of tangent of y is secant squared of y times dy over dx. And now I could solve for dy dx, and I get that dy over dx is equal to 1 over secant squared of y. But 1 over secant squared of y is otherwise known as what? Yeah, this is cosine squared of y. And now what's really interesting is, again, like we know that tangent of y is x, so we could use a reference triangle right now. Let's see. What's a good way? So if I know that tangent of y is x, then tangent of y is equal to the opposite over the adjacent. So the opposite, if this thing is y, then this is x and this is y, right? And so what's this side? I guess it would be the square root of 1 plus x squared, correct? Interesting. Okay, so now the question is, what's cosine of y? Cosine of y is the adjacent over the hypotenuse. The adjacent is 1. The hypotenuse is square root of 1 plus x squared. So you get 1 over the square root of 1 plus x squared, quantity squared, which is 1 over 1 plus x squared. Little bit of a side note, but basically what we just figured out is that the derivative of y, which was tan inverse of x, dy dx, is 1 over 1 plus x squared. And you could do that for all inverse trig functions in a very similar way, and you get all of their derivatives. So, and then it's just because, well, I know that that derivative is this guy, so his antiderivative must be this guy, right? So just going backwards. That answer your question? A little bit of a long-winded answer, but yes.
Right. Yeah, I was curious on one of your example problems. You're basically saying that as it was tan inverse of e to the b, and as b goes to infinity.
Okay.
You were saying it would go towards pi over 2.
Yeah, so you said I had like tan inverse of e to the b.
As b goes to the limit.
So the limit of this is b goes to infinity?
Yes.
Yeah, and I said something about, okay, so as b goes to infinity, e to the b goes to, well, infinity. And tan inverse of infinity, well, you have to kind of remember what tan inverse looks like. So the graph itself looks like this. It kind of goes up this way and down this way, and there's an asymptote here. There's an asymptote here. This is pi over 2. This is minus pi over 2. And so as this thing gets really, really big, this x value, the y value gets closer and closer to this asymptote, which is pi over 2. Does that make sense? Yeah, so this is just knowledge of that function shape. Yeah. Other questions? Yeah.
Page 14.
14? Okay. We have the integral of x to the minus 2 plus x to the minus 3 divided by x to the minus 1 plus 16 x to the minus 3 dx. All right, well, it's a little bit of a mess, but so there's a couple ways that we could go about this. I think that the cleanest is to actually just use algebra on it. I don't know that there's any like really clever thing. The thing I'd like to do in some ways is I'd like to say, oh, let's just use sub for x to the minus 1, which maybe you could even do. If you did, just let me think this through for a second. So if I said that this was basically 1 over x, then what's du? So that's x to the minus 1. So it would be minus x to the minus 2. So I'd need a minus x to the minus 2 somewhere here. I guess I could factor it out of the top. Is that correct? So I could factor x to the minus 2 out of the top and then get a negative in there and get it done that way. So yes, that is one way I could go. The other way I could go is I could just write these as like 1 over x squared, 1 over x cubed, 1 over x, 16 over x cubed, and then kind of simplify that into something that like looked better. But this does work. Maybe we should do this just because it looks kind of fun. So if I did factor out x to the minus 2 on top, I would get x to the minus 2 times, then what would be here, I guess 1, and then plus x to the minus 1. So if I multiplied that through, I get x to the minus 2 plus x to the minus 3, which is perfect. And on bottom, I just have x to the minus 1 plus 16x to the minus 3 dx. But I need a negative to get my du. So I'll have to put in the negative, which means I have a negative on the outside as well. Now I could make the substitution if I want to, and I get a negative integral. This is part of du. This is part of du, this is part of du. So what's left over on top is 1 plus u. And on the bottom, I have u plus 16, I'm sorry, plus 16u cubed du. And now the question is it actually any better? Or is this just a terrible thing as well? It's not my favorite thing ever, but we could factor out a u on the bottom, correct? If I did, I'd get the integral of 1 plus u divided by u times 1 plus 16u squared du, and there's still a negative out here. This problem, what could we do to that? What does it look like? Yeah, it looks like partial fractions. So I would say, okay, if this is where you go, then this would be a good time to use partial fractions to break this up into two different integrals that probably you could work both of those. If you went the other way and you wrote this all out as 1 over x squared, 1 over x cubed, maybe you wouldn't need the partial fractions, maybe you would, I don't know. But this is one way to go, but now that's a partial fractions problem. Do you want me to keep going, or do you feel like this is enough to get you started? Shoulder shrugs. Me.
You set up like
The partial fractions?
Yeah.
Sure. So this is a linear, because it's just all by itself. And then this one, I cannot factor because of the plus. If it were minus, I could. Since it's a plus, I cannot. So that's an irreducible quadratic. So if I were doing my little side work over here, I'd get that 1 plus u divided by u times 1 plus 16 u squared would be equal to, the u just gives me an a over u. And the 1 plus 16u squared gives me 1 plus 16u squared. That's an irreducible quadratic. So this is going to be bx plus c. And that's how you would get it started. And now, of course, clear all the fractions, solve for a, b, and c, yada, yada, yada. So we can keep going at this point, but I think you could do it. I don't want to take all of your fun. Other questions?
you just like start 15.
Sure. 15. Let me see. Okay. So integral from 1 to 4 of 2 to the power square root of x divided by the square root of x dx. Okay. Interesting. So what I'm seeing here is square root of x. I'd kind of like to get rid of the square root of x. It's not very nice. And maybe I could use substitute for the square root of x. Let's see what happens if I do. So if I let u be the square root of x, then du is going to be, this is x to the 1/2, correct? So this would be 1/2 x to the negative 1/2. Which could also be written as 1 over 2 square root of x dx. That's very, very close to what I do have already, correct? I have 1 over the square root of x dx. I need a 2 on the bottom to make this work. So I could just put my 2 in right here. And that means that's a 2 on the bottom. So I also need a 2 on the top to cancel it out. And now we could substitute. And if I do, the 2 stays. I get the integral of, I need this one. Don't put a u here because that's part of the du. The 1 over 2 square root of x dx. That's all du. So I just get 2 to the u du. And then I need new limits of integration. So I need to say, okay, if x is 1, u is 1. If x is 4, u is 2. And now I guess we have to remember what the antiderivative of 2 to the u is. Does anybody remember that one? Yeah.
Is it like, I think A over ln of something like that?
So it's 2 to the u, and I think somebody was saying it, over what? Over ln of 2, that's right. So it's 2 to the u over the natural log of 2. And then I need to evaluate that from 1 to 2. So that just gives me 2 times 2 squared over ln 2 minus, plug in 1, I just get 2 to the first over ln of 2. Yeah, so this is 2 times, this is 4 minus 2 over ln 2. So that's just 2 over ln of 2, or 4 over ln of 2. Yeah. Other questions? This is probably the best section in the book, and I didn't assign every single problem or anything, but this is a great section to practice for the exam. So if I were studying for the exam, I'd just like pick a problem out of here and see, can I do it? And if the answer is yes, it's like, well, awesome, good job. If the answer is no, then you know, wait, I haven't quite got the hang of one of the sections. So, and there's really 2 parts to any of these problems. The first part is saying, is this one of the types that we've studied? Is this integration by parts? Is this partial fractions? Is this, yada, yada, yada. And then once you know which of them it is, then you need to do it. And actually, I kind of feel like the doing it part, it still is something, but it's actually not the hard part. The hard part on this particular exam that you're coming up against is the diagnostic part. So just make sure that you can diagnose, and it's not enough when you're prepping for this exam to just say, okay, here's a partial fractions problem. Let's see if I can do it. It's like, even if you can, that's not good enough. You have to be able to know this is a good partial fractions problem, or this is a good integration by parts problem. Let's try it. Also, sometimes you have to make a u substitution to get it into the form where you're ready to do the thing, whatever that is. So it just takes practice. So I would just say work problems, work problems, work problems. That's the way to get ready for this exam. Yeah.
So the previous question that you did
Yes.
had 2 different ways to do it, like, not this problem.
Oh, not this problem. Yeah, yeah.
So would you mark us down if we chose one way or the other?
No.
So just if we complete it?
Yes.
Okay.
Yeah. I'm not going, if there is more than one way to do a problem, I'm certainly not going to mark you down for choosing one way over the other. No. Other questions? Yeah.
You said it, number 16.
16, look. So we have integral dx over x to the 4th minus 1. Okay. So this, is this 16, did you say?
Yeah.
Integral dx over x to the fourth minus 1? Or was it plus 1? It's minus? Okay, good, because I thought this is going to be harder if it's plus. Okay, so x to the fourth minus 1. Yeah. Okay, so the first thing that I see in x to the fourth minus 1 is x to the fourth minus 1 can factor. So let's factor it. And if I do, I get the integral of dx. And on the bottom, I get x squared minus 1, x squared plus 1. Right, so we have difference of squares. And then the question is, do either of these factor? Yeah, which one? Yeah, the one with the minus, right? That factors again. And I could write this as dx over x squared minus 1 becomes x minus 1, x plus 1. And then this one just stays x squared plus 1. And now I think it's fairly clear what type of a problem this is, right? This is partial fractions. We've got a linear term, and an irreducible quadratic term. So if we were setting this up and trying to substitute, we get 1 over x minus 1 times x plus 1 times x squared plus 1 is equal to a over x minus 1 plus b over x plus 1 plus cx plus d over x squared plus 1. And now we need to do the things. But this is how we would get this started. Other questions? Yeah.
11.
Uh-huh.
I was thinking, so secant x minus x squared.
Yes.
Would you think like this secant is 1 because somehow we'll find 1 to combine them first? And then
Yeah, I think my first thought is just multiply it out to start. So if you squared that, you get a sine squared of x. That's good, correct? Because sine squared of x, we know it's antiderivative. Then that you'd get 2 times secant times cosine, well, negative. Negative 2 times secant times cosine, but that's negative 2. And we know that negative 2 is antiderivative, so that's good. And then we would get plus cosine squared of x. But okay, I don't know the antiderivative of cosine squared of x, but I do know the half angle identity. So I could use a half angle identity sub in for cosine squared of x, and then I could get the antiderivative. Does that make sense?
Yeah.
Yeah, that's good. Other questions? Everybody kind of looks like it's Monday. Sad but true. Everybody kind of looks a little bit glazed over. It's all right. I feel your pain. Anything else you'd like to do while we're here? Yes.
Can you solve that?
Can I keep going?
Yeah.
Sure. So if I multiply this out, so I want to multiply both sides by this denominator, correct? So I get 1 is equal to, okay, it would be a times x plus 1 times x squared plus 1 plus b times x minus 1 times x squared plus 1 plus cx plus d times x minus 1 times x plus 1. Correct? Okay, so now we can say, are there nice guys to plug in to help me? And I think in this case, there are a couple. We could plug in 1, we could plug in minus 1, correct? So let's say that x is equal to 1 and see what happens here. So if x is 1, this side is just 1. So I get a 1. And on the other side, if x is 1, this term goes away. This whole term goes away. This one does not. So I get a times this is a 2, and this is a 2. So I get 2 times 2 times a. So 4a. So I get 1 is 4a. And so a is 1/4. The second helpful thing is that x could be -1. And if x is -1, I still get a 1 on the left side. And -1 gets rid of what? I guess -1 gets rid of this term, -1 gets rid of this term, and I'm just left with this term. So if I had -1, I'd get -1, -1, so this would be -2. And then I get 1 plus 1, which is +2. So 2 times -2 times b is -4b. So I get b is -1/4. And now I could do whatever I still need c and d, correct? So I know a and b, I need to get c and d involved. Any suggestions?
0.
So are you saying plug in 0?
Yeah.
You could plug in 0, yes. So if you plugged in 0, what would you get? So we're saying, let's just let x equal 0 and see what happens. Then you would get 1 on one side. On the other side, you would get, this is 1 times a. So a plus, let's see, if you plugged in 0, you'd get 1 times -1 times b, so -b. And then over here, if you plugged in 0, you'd get 1 times -1 times, okay, if we plug in 0, I just get d. So -d. And we know what a and b are. So we get 1 equals a, which is 1/4, minus -1/4. So that's +1/4, minus d. I can subtract a half from both sides, and I get a half is equal to -d, and d is -1/2. But we still don't know what c is. So how could we get c? We need to plug something in or use a power of x that's going to show up with c in it. There's a couple ways you could go. The other thing you could do, if you wanted to, is you could just plug in some other value of x, because now you know a, b, and d. Or you could say, what's a power of x that's going to show up with c in it? Well, there's c times -1 times +1, which is just x. So maybe I might look at the x terms on both sides of the equation. That will get the job done. So if I just looked at the x terms on both sides, there are 0 x terms on this side. How many x terms on the other side? Okay, so the question is, can this thing produce an x term? And how many of them?
3a.
It can produce a of them. Does everybody agree? Because it's a times x times 1. That's the only way I see to get an x, is a x times 1. So just a of them. How about this term? Can it produce an x? Yes, it can go b times x times 1. So b of them plus b. And then we move over here. Can this thing produce an x? Yes, And I think it can do it in several ways, actually. We could get cx times -1 times +1, which is negative c. Is there another way to get an x using the d? You could get d times x times 1, or you could get d times -1 times x. But those cancel, and so you just get no d's. Or you could say you get plus d and minus d. Either way is fine. But either way, it's gone, and this is what we're left with. So 0 is a, which is a fourth, plus b, which is minus a fourth, minus c. So we get 0 equals minus c, and c is 0. Okay, so now we can rewrite that integral. And we would get that the integral, so here, moving here, is the integral of a over x minus 1. A is a fourth, so I get 1 over 4 times x minus 1 dx. I'll just split these up into 3 different fractions. Then I get b over x plus 1. B is -1/4. I'll put the negative outside. I get integral of 1 over 4 x plus 1 dx. And then finally, c is 0, so I'm not going to get an x term on top. D is -1/2, so I get minus integral 1 over 2 times x squared plus 1 dx. Hopefully, I'm still writing on the board in a place people can see. Yeah, I am. Okay, and now we just need to take the antiderivative. Antiderivative here, I get 1/4. It just hangs out because I could move it outside the integral. And this is just ln of absolute x minus 1. Second one, similarly, the -1/4 just hangs out. I get ln of absolute value of x plus 1. And then this one's a little bit different. The -1/2, again, is just hanging out. But now I have 1 over x squared plus 1. Its antiderivative is tan inverse of x plus a constant. And that's it. Yeah.
Sorry, I don't quite understand the x terms when you're saying like I don't
Yes.
understand how that works.
Right. So you get what I'm doing here, just plugging in a number.
Yeah.
But what's going on when I go to like
Yeah.
the x terms?
Yeah, exactly.
Yes. Okay. Yeah. What I'm doing is I'm saying it's very powerful that I'm saying that these two sides are equal. What I'm saying is that all of the x squareds on this side are equal to all of the x squareds on this side. And all of the constants on this side are equal to all of the constants on this side, and et cetera, right? And what I see here is that all of that nonsense right there equals 1. There are no x's that stay, or x squareds or x cubes. They're all gone once you add them all together. So what I know is like, okay, so how many x's are there over here? None. Do you agree with me?
Yeah.
So what I'm saying is I'm going to use the fact that I know that there are 0 x's on both sides of the equation to help me to solve for something. Because I know there are 0 x's over here. Just look, 0 of them. But I could write it if I wanted to. I could say it's 0x plus 1. Right? So 0 x's equal some number of x's over here, which is 0 of them. So I need to know how many x's are there over here. Whatever it is, that's what I figured out. There are ax's plus bx's minus cx's. That has to be 0.
Okay.
So in some sense, I'm leaving off the x term, because what I really figured out is that 0x equals ax plus bx minus cx. That's what I really said. But I just kind of divided through by x, so to speak, to get that nice equation. Does that make sense?
Yeah, no, that makes sense, thank you.
If you want to do it, that's to the third, to find that. See about it.
Say that one more time.
X to the third. To
Yeah,
find
I
C
did
value.
that.
X to the third. Oh,
Think about it.
use the x to the third.
Yeah,
Oh yeah, that would have been fine.
I think it's more.
It probably is much better. I don't know why I used x. It just felt like the right thing to do at the time. But you're probably right, because then you get an A plus B plus C. Yeah, that would be better. Yeah, that would have been a better choice. Other questions? One thing that's interesting though about this method using the x's and using the numbers is the x way always works. The number way does not always work, or it's very, very terrible in some situations. When it works though, it's easier. So it's kind of like if you see some obvious ways to cancel and make something zero, do it. It makes life a lot easier. But if there isn't, like if everything's like irreducible quadratics and stuff, sometimes there's no way to make anything zero. And so then the only way to do it is to use the powers of x.
Okay.
Yeah. Other questions? All right. Well, if not, we will end there. So there is an assignment due over this section, due tonight at 11. And then next time we'll start talking about improper integrals. Okay, so watch the videos over improper integrals and start the first assignment for Wednesday. Have a good day. Yeah.
I know that we did 14, but I worked it out a little bit further and then got started again.
Okay.